Thanks the organizer for inviting me here and being able to speak about recent advances on osteoarthritis in my group. Osteoarthritis is a highly prevalent multifactorial joint disorder and a major cause of pain and disabilities worldwide. It is deemed to affect almost 10% of men and 18% of women worldwide, with a high economic burden, which is with an increasing trend due to the aging of the population. To make this scenario even worse, there are no effective therapies to cure osteoarthritis, being the main therapeutic options palliatives to alleviate the symptoms, and the prosthesization of the joint is the final option for end-stage disease manifestations. OA, the cartilage breakdown and fibrillation is the most evident sign of the pathology, but OA has been recognized as a whole joint disorder affecting the subchondral bone, which is altered with the formation of osteophytes. There is the synovium, which is inflamed, and there is the hypertrophy of the capsule of the joint. And despite recent advances, the pathogenic mechanisms behind the pathology are not known. Obesity, kinematic misalignment, injury of the joint are all risk factors which contribute to the damage of the surface of the joint, which fail to absorb and distribute the mechanical load to the joint itself. And the current human preclinical models rely on bidimensional or three-dimensional chondrocyte cultures with the addition of cytokines or ex vivo explants, and all of these fail to recapitulate the clinical markers. Why that? Because they are failing to recapitulate the in vivo mechanical milieu in which the mechanical load has been recognized as one of the main factors for the onset of the pathology. Therefore, to design new in vitro models, we need to take into account the mechanical load. That is what we have done in the past years when we designed this device, which is made of 3 layers of PDMS. The top layer is a cell culture layer, the bottom layer is an actuation chamber, and those layers are separated by a thin PDMS membrane. When the bottom layer is pressurized, the membrane deflects upward, and the culture layer is made of overhanging post with a gap, a small gap, which is a stop end for a stroke, a stop end. So the mechanical load turns out to be a compression of the three-dimensional cells in this culture layer. This technology has been patented and is now commercialized by Biomimics, and so I have to disclose that I share equities in the company. Okay, so to design the right compression for this model, we took advantage of the periodicity of the cell culture layer. We implemented a finite element model, and we were actually able to benchmark that against experimental values, so that we could actually say that our model is able to impose an homogeneous confined compression, which can be tuned by selecting the gap size into a physiological compression of about 10% or a hyperphysiological compression of about 30%. So the model was we started using the model generating a healthy cartilage, starting with primary chondrocytes cultured in a chondrogenic media inside a polyethylene glycol gel modified. And after 2 weeks of culture, we could actually see a nice deposition of the most important components of DCM, collagen type 1 and 2, and aggrecan. And the ratio between collagen 2 and 1 increased over time, reaching almost the value of the native cartilage. As well, we could actually measure the GAG production in the metrics. Also, from the gene level, we could see an increase of the an overexpression of the aggrecan and the lubricin, an increase of the genes correlated to the embryonic development of the cartilage, and an increase as well of the so-called breaks of the hypertrophy, which are the Fritz and Garvelin-1 genes, which are antagonists of the Wnt and BMP pathways. So after achieving a stable and mature cartilage, we started the compression. So either a physiological or hyperphysiological compression, and of course we used a static condition as a control. So what happens is that there is a increase in the gene related to degradation and inflammation of the matrix, like metalloproteinase 13 and interleukin 6 and 18. And that is the collection of pre-inflammatory MMP13 was collected in the medium, and that translated into the degradation of the matrix with the degradation of collagen type 2. Also from the anabolic point of view, we saw the loss of cartilage component in matrix, collagen 2 over collagen 1, and aggrecan in the hyperphysiological confined compression. Finally, the switch from the stable cartilage to the hypertrophic cartilage is one of the most important clinical hallmark of the osteoarthritis, and therefore we looked for genes related to that, so collagen 10 and Indian hedgehog, which were actually increased only in the hyperphysiological compression. The same thing happened to the decrease of Fritz and DKK1 and Gremlin-1 genes, which are clinical markers, so that this result is clinically interesting. And this can be only achieved, the hypertrophy, only in our model with mechanical compression, which cannot be re-achieved in traditional 2D or 3D cultures with addition of cytokines. So now we have OA traits, and we selected 2 drugs which have the effect of decreasing the inflammation and the degradation. And actually that was observable in our model. And again, that is not really observable in traditional 3D models. So we designed a cartilage on chip model, but which is able to recapitulate the clinical traits of the osteoarthritis. But as I said in the introduction, the OA is a full joint disorder. So we try to model the osteochondral unit, taking into account also the fact that the mechanical load is not constant. So there is a gradient from about 35% on the cartilage down to 1% close to the bone. And if we take a histological picture of the joint, we can see that there's the cartilage, then there's chondral bone, and in the middle there's the calcified cartilage there, which during OA expands and get vascularized. So we introduced a new concept which we called vertical burst capillary valve to add up a new layer, so a 2-layer device, which is here with a picture, cross-section, some SEM, and the sequential operation, so a sequential injection of the 2 gels, which actually create a neat interface, which is horizontal, so one on top of the other. And you can understand that we can now apply a mechanical load on both of them. So again, we went back to the modeling. We did some IT AFM to get mechanical properties of the pure gel and the gel with cartilage. And we used that to model geometrically both the PDMS and the gels. And we came up with a final geometry which is able to impose a 30% compression in the cartilage compartment, while it was able to impose about 3% in the calcified cartilage compartment. So to test whether this can be also translated into something measurable in terms of cells, we see the 2 cell types, in one labeled in green, the same cells, so chondrocytes in the cartilage and in the calcified cartilage compartments. And we observed some expression of genes. And actually, the C-Jan gene was overexpressed only in the bottom compartment, and that was also correlated to the release of degradation and inflammation markers only in the bottom compartment. So that is what actually we were looking for. So this means that we were able to catch something in the pathway of the TRPV4 mechanism of action. Furthermore, we want to assess whether the mechanical modification of the calcified compartment was per se affecting the bottom compartment. So to do so, we made a surrogate of the calcified compartment, calcified cartilage compartment using gel seeded with different concentrations of beads. And once again, we could see that the presence of beads were actually affecting the bottom compartment with gene expression and the release of inflammation markers. So the model was validated in our opinion. So we went on using real cells for the calcified compartment as well to understand whether the calcified cartilage was affecting the cartilage itself. So we optimized the medium. For the calcified cartilage, we used the bone marrow MSCs, and we used the chondrogenic medium and an osteochondral medium in single chamber device to start with, and in a simple bidimensional, or actually bilayer device. And in the single devices, we could see that both culture media were responding as expected, but if you look on the immunostaining here, you can see that only the osteochondral medium is able to make the cartilage compartment expressing the collagen type 2, at the same time expressing mineralization in the calcified cartilage. So we picked up that culture medium. And also here you can see that the two-layer compartments in which you have the collagen 2 in both compartments and the mineralization only in the calcified compartment only. And interestingly, you can see here for the anabolic behavior that there is a synergistic effect of the presence of the two cell types, which actually adapt something which is not seen in single cultures. So this is something that must be investigated. So we then translate it in our osteochondral unit device, so with the horizontal interface, and in the top there is the calcified cartilage, in which there is mineralization, and in collagen 2 is expressed everywhere. Once again, adding the compression, so we start to compress these two layers, we could see a protective behavior of the two cultures, which are synergistic as compared to single cultures. So to close the circle, we try to understand whether the vascularization is affecting, or actually we can study the effect of the vascularization on the onset of the pathology. To do so, in the calcified compartment, we added UVEC cells. And what we observe is the loss of cartilage phenotype. Collagen 2 here is not anymore present, and instead there is the acquisition of a mural phenotype on the calcified cartilage compartment with the expression of alpha-SMA and laminin, which actually support the growth of vessels in that compartment. Here, to understand the expansion of the calcified cartilage, we seeded the mesenchymal cell with UVECs and leaving empty the half of the simple bilayer device. And here what we observe is the presence of VEGF, so meaning that there is a migration, an invasion of the cells into the empty compartment. And this is not, of course, seen when we seed chondrocytes there. Why that? Because the chondrocytes are known to protect the cartilage, is a vascular and a neural tissue. So this is a protection, and there is no expression, no migration of cells into that compartment. But what happens when we apply a mechanical load? So this is, again, cartilage, healthy cartilage, and calcified cartilage on the top with the UVEX. And these are very preliminary data, so got like last week and added for this event. All these is unpublished. So there is the expression in the bottom compartment after 14 days, so after the maturation of the cartilage of collagen type 2, so cartilage is mature, and lectin, which is a protective proteins which prevents the vascularization. But after 14 days of culture, we see a partial loss of the collagen 2 and a partial loss of lectin 1, which is accentuated by the compression. So this, again, something that this means preliminarily that we are trying to, and actually succeeding to onsetting the osteoarthritis there. When we are currently investigating the possible invasion of vessels into the cartilage compartment. Oh, this should not be there. Okay, to conclude, I showed a couple of devices, MPS devices, able to generate OA traits in a simplified only cartilage compartment or in a more complex osteochondral unit compartment. And all these were possible only by the application of mechanical load. So no cytokines, no anything else in a 3D environment. The construction of a biphasic device is actually pivotal to understand all the steps, all the causal relationship effects of the OA, which is still mainly unknown. And of course, these devices can be used to investigate the pathways. We are actually currently investigating the pathways of the onsetting of the OA thanks to single cell RNA-seq currently. And with this, I really would like to thank all the people from my group. Paolo Chetta, who is going to present our work in this room in a while, so stay here. And also our collaborator in Switzerland, in Basel, Andrea Mainardi, who did most of the work. And I have to say that we are actually hiring, in Basel, we are hiring someone, a postdoc, to go on with this project. So if you know someone good, just let him contact me. And I thank you for your attention. Thank you.